Hello everyone, and welcome to our presentation on HVAC design and code compliance in data centers. Today, we'll explore how proper HVAC systems ensure optimal performance and safety in these critical facilities. The title might seem technical, but don't worry. I'll guide you through the key concepts. We'll cover topics like load calculations, system integration, chilled water systems, cooling units, and thermal safety measures. So, let's get started and dive into the essentials of designing reliable, efficient data center HVAC solutions. All right, let's take a closer look at the feed design parameters, specifically for this data center example. First, we have the mass flow rate. Denoted as M, this is calculated using the formula M equals Q divided by the specific heat capacity, Cp, times the temperature difference, delta T. In this case, Q, the heat load, is 1,580,000 units, presumably in watts or BTUs. Cp, the specific heat capacity of water, is 4.186, and the temperature difference we're working with is 5 degrees. Plugging those numbers in, we get M equals 1,580,000 divided by the product of 4.186 and 5. Which results in approximately 75.5 kilograms per second. This tells us the amount of mass flow needed to transfer that heat load effectively. Next, each chiller is rated at 225 TR, tons of refrigeration, and they're configured with N+1 redundancy. That means we have one extra chiller on standby, ensuring continuous operation even if one unit needs maintenance or experiences a fault. Now let's look at the broader context. This slide connects to the feed stage, which is all about initial design and planning. Then, the load analysis helps us understand the cooling requirements. The chiller's capacity and redundancy are key to ensuring reliability. Airflow management and adherence to ASHRAE standards are also critical, as they influence efficiency and equipment longevity. Overall, these parameters set the foundation for designing a resilient, efficient data center cooling system. Let's take a closer look at the codes and standards that guide our compliance efforts. On this slide, you'll see the calculation V equals Q divided by A, which gives us a velocity of 5.1 meters per second. This is important because it falls within the ASHRAE 62.1 limit of 6.5 meters per second, ensuring safe and efficient airflow. Now, these standards, such as ASHRAE 62.1, ASME B313, API 505, NFPA 90A, and ISO 14644, each play a critical role in different aspects of our design and safety protocols. For example, ASHRAE 62.1 focuses on ventilation and indoor air quality, while standards like ASME B313 and API 505 address piping and pressure vessel safety. ISO 14644 is key for cleanliness and contamination control in cleanroom environments. By adhering to these standards, we not only ensure compliance but also optimize safety, quality, and performance throughout our projects. Remember, understanding and applying these codes is essential to maintaining the integrity of our systems and meeting industry requirements. Let's walk through the HVAC design workflow. First, we start with understanding the pressure losses in the system, which are represented by delta P ducts, delta P filters, and delta P diffusers. When you add these up, they should balance out to 0, meaning the total pressure drop, or SB, is about 0.9 inches of water gauge. Next, to determine the fan power needed, we use this key formula. Fan power in horsepower equals the total pressure SB multiplied by the flow rate, divided by 6356 times the fan efficiency. This helps us size the fan correctly for the system. Throughout this workflow, there are several critical steps. We begin with the calculation phase, where we quantify the pressure drops and power requirements. Then comes the selection process, choosing the right components. After that, we move to creating a 3D layout to visualize the system. We also review the design against building codes to ensure compliance, and finally, we seek approval to move forward. This workflow is essential because it ensures that our HVAC system is both efficient and compliant, ultimately supporting the overall goal of delivering comfortable, reliable indoor environments. Let's talk about material selection and quality control, which are crucial for ensuring safety and reliability. First, we set our testing pressure, P-test, at 1.5 times the design pressure. Since our design pressure is 10 bar, that means P-test equals 15 bar. This overpressure testing helps us verify the integrity of the materials and welds under stress conditions beyond normal operation. We also inspect welds using radiographic testing, or RT, with about 10% of welds selected for inspection. Additionally, we perform hydrotesting at the same 15 bar pressure to double-check the weld quality and detect any potential leaks or weaknesses. On this slide, you'll see icons representing key aspects: materials, QA/QC, welding procedures, testing methods, and insulation. Each of these plays a vital role in ensuring our system's overall integrity. Remember, the combination of proper material selection and rigorous quality control is what keeps our projects safe and efficient from start to finish. Now let's look at HSE and risk compliance. First, the ACH, or air changes per hour, is calculated using this formula. ACH equals Q times 60 divided by V here. Q is the airflow rate, which in this case is 10,000 cubic meters per hour, and V is the volume of the space, 50,000 cubic meters. Plugging those numbers in, we get 12 ACH. This means we're exchanging the air in this space 12 times every hour, which is important for maintaining safety and air quality. Next, regarding H2 levels, it's crucial that the hydrogen concentration stays below 1% of the lower flammable limit, or LFL. Staying under this threshold ensures explosion safety, as hydrogen is highly flammable and even small amounts can pose risks. Now on to the icons and symbols. The risk warning, ventilation, explosion-proof measures, safety protocols, and BMS control. These elements work together to create a comprehensive safety system. The risk icon reminds us to always assess and manage potential hazards. Ventilation is key to controlling gas concentrations and preventing dangerous buildups. Explosion-proof equipment ensures that even if gases are present, they won't ignite and cause damage. Safety measures are our first line of defense, and BMS, or Building Management System Control, helps monitor and automate safety protocols in real time. All these points connect to our overall goal: maintaining a safe, compliant, and efficient environment. Let's take a look at the documentation and deliverables for this phase. As you can see, the supply and return system has achieved a positive pressure of 1.02, which is a great indicator of proper system functioning. Now, the documentation package includes a comprehensive set of items such as drawings, the bill of quantities, inspection test plans, datasheets, and the compliance report. These are all crucial for verifying that everything has been executed according to the specified standards. You'll notice the icons representing different deliverables: drawings, BOQ, submittals, ITP, and the code matrix. These elements are essential for ensuring transparency, clarity, and quality control throughout the project. In essence, this slide emphasizes the importance of thorough documentation, not just for project approval, but also for ongoing maintenance and future reference. It ties back to the overall theme of delivering a reliable, compliant, and well-documented system that meets all the project requirements. Now, let's look at value engineering and optimization. Here, we see that the new delta P, or pressure drop, is reduced to 0.92 times the old value. This means we're achieving a significant decrease in pressure loss, which directly translates into energy savings. In fact, we're looking at about a 12% reduction in energy consumption, and the return on investment is around 5 years. That's a pretty compelling case for implementing these improvements. By designing more efficiently, we not only lower energy costs, but also enhance system reliability. Efficient design is at the core of this approach, ensuring that the system runs smoother and with fewer issues over time. You'll notice the icons here: optimization, energy saving, innovation, monitoring, and efficiency all represent key aspects of this process. Optimization involves fine-tuning the system, energy-saving emphasizes reducing consumption, innovation pushes us toward new solutions, monitoring helps us keep track of performance, and efficiency ensures we're making the most out of every component. Altogether, these elements connect back to our overall goal: creating smarter, more sustainable systems that deliver long-term value and resilience.